All right, let's talk about impulse and momentum. Actually, I should have written here the impulse momentum theorem because that's what this is called. I'm abbreviating it. I will just be talking about impulse and momentum and not using big fancy words because I'm not a fancy guy. So let's talk about impulse and momentum. The first thing that I want to talk about is that we do have a couple different ways to define impulse. The first way that we can define impulse, is using this change of momentum idea. That's all it is. So if impulse is the change of momentum, then m delta v would also be the change in momentum, or it would also be the impulse. So one way, and this is the one that kind of trips students up sometimes, to figure out the impulse is to figure out what the change in momentum is. So that'll show up on AP questions where they'll tell you the mass before, and they'll tell you the velocity before, and they'll tell you the mass after. Well, the mass after is not going to be different. They'll tell you the velocity after, and they'll say what was the impulse here? Did it have a positive or a negative impulse? That kind of thing. And you'll look at it and you'll be like, oh no, I don't have enough information because I know that the formula for impulse that I memorized was F delta T, and they didn't tell me anything about force and time. But if they gave you mass and velocity and they gave you what the velocity changes were, you can always figure out what the change of momentum and therefore the impulse is. So keep that in mind that even though this first equation doesn't exist on the formula sheet, it's implied to be there because they write delta P as impulse. So anything that changed the momentum would be that. So this second equation is on the formula sheet. But if we combine them together, we get the impulse momentum theorem. And that basically just says if, this is the transitive property, if A equals B and A equals C, then B equals C. So we can say M delta V equals F delta T. But what's useful about this whole combined equation, and it's a very common equation that you'll be expected to use, is we can start looking at the relationship between four different variables. So one thing we could talk about is we could talk about you have a really, really big truck. And if that big truck is moving, it's probably going to require a lot of force to stop. Unless we wanted to spend a lot of time stopping it. So if we had this variable here was really big, then we'll either need a big force or a lot of time, or maybe we just need a medium amount of both. Those all work. We could also say that if something's moving really, really, really fast, we're either going to need a lot of force to stop it or a lot of time to bring it to rest. And if we have something that's both massive and moving fast, then it's probably going to require a lot of force and a lot of time to get it to rest. So these are equations that come up a lot, but one thing that I want to point out is this relationship between force and time. Specifically, if force, no, that's the wrong way to say it. If we want to get something done very, very quickly, it's usually going to require a lot of force. So an example of that, and we'll talk about this, I'm sure, in class, is if I get in a car accident, I have momentum that will be changing. I have my mass moving at the velocity of the car that by the end of the car accident will be zero. So I have an impulse, I have a change in momentum, but I have two options of how this happens. I can either have the collision take a long time, like slowly applying the brakes, and that means that I don't have much force on me. Or I can have this happen really fast by slamming my head through the windshield. In that case, the collision is much faster, but that means the force must be much greater. When you wear a seatbelt, the advantage of wearing a seatbelt is that the collision takes longer because instead of you going smash with your forehead, you go, and then you come to rest. And all of that extra time as you're moving forward, as the seatbelt slightly flexes and bends with you and brings you to rest, means that you can dramatically decrease the force. It doesn't take much. If a car accident usually happens in the scale of 0.001 seconds, and we can just make it take 0.005 seconds, then we can decrease the amount of force that somebody's experiencing by a factor of 5. We don't have to change it by very much to make these kind of collisions much, much safer. So that's the impulse momentum theory right there. It relates the mass and velocity, the ideas of these changes of momentum, to the impulse being provided by force exerted over a period of time. Okay, so there are some graphs that I want to talk about here. This one here is really obviously an impulse graph. I have force versus time, and we just saw that impulse is force times time. So this area under the curve here must be my impulse. The other graph that I have here is a similar graph. It's a force versus displacement graph. And the area under the curve here has nothing to do with displacement or with momentum. Instead, it's work. But the reason why I bring this up is both of these graphs can be used to figure out the final velocity of an object. If we are given the mass of the object and its initial velocity, then with this graph here, we could figure out how much change of momentum happened. So we could do m v naught plus delta p, and we know that would be equal to m v final, and we could just solve for the final velocity. If we're given this problem here, where there's work applied, then we would do this with an energy formula, and we'd say, okay, we know the initial energy plus the work, that's the area under there, is going to be equal to whatever final kinetic energy it has, 1/2 mv final squared. And then we're solving for Vf. So either way work, and actually the way you use them is pretty similar, although there's a lot more squares and halves and stuff, so the energy one's a little bit uglier. But just be aware that both of those options exist for finding final velocity, and they'll often either give you one of these graphs or the other, or sometimes both, and either ask you to do that or ask you which graph and how you would use the graphs to do it. So now you know. Make sure you take notes on that part. Rewind if you have to. Last thing that I want to talk about is when to use conservation of momentum, conservation of mom, and when to use impulse. Conservation of momentum works really well when we know both objects. We have two objects, and we can really easily figure out their speeds and energies and stuff like that. We want to be looking for a, oops, that didn't work out at all. We want to be looking at a closed system. Oh my gosh. We want to look at a closed system. If we're doing an impulse problem, usually we're going to be talking about one object. We're talking about, Mr. Terrell in a car accident coming to rest, and then we're going to be talking about F delta T type thing. This tends to be when there's outside forces acting on your object. So if you're not sure which one to use, you can kind of think through: am I easily able to close my system and account for the energies and momentums of everything, or are there outside forces that I can't account for easily, or objects outside that are going to be acted on that I can't account for? And in that case, you're going to use impulse. So that's what you need to know about impulse and momentum. Thank you very much, and have a great evening.